I owe you a lab test and an exam now. I'll try to get them back by Tuesday. Okay. And a quiz? Okay, I'll try to get it back by Tuesday. So we have to get through two things today so that you can do all these Newton's second law problems. So first we're going to do an approach for rolling and sliding along non-horizontal surfaces. So if you have objects rolling or sliding along horizontal surfaces, the math is pretty easy. This is a way to simplify the math a little bit if the surface isn't horizontal. And then we have to talk about friction. We haven't talked about that yet. Okay, so first, so here's a trick for rolling and sliding along non-horizontal surfaces. And what you do is we're going to choose a new coordinate system. So choose the positive y-axis to be straight out of the surface. And then the x-axis, that means, is parallel to the surface. So, for example, if you have an object rolling along an incline like this, we'll make the y-axis point straight out. And then you choose the x-axis. There's only one x-axis that works with this y-axis if you follow the rules of coordinate systems, so it has to be this way. Remember, a coordinate system has to be a rotated version of the one that we're used to. So you can rotate it like this. If I had made the y-axis point up and the x-axis go that way, there's no way you can rotate this coordinate system to make it do this without flipping, and that's not allowed. So let's do a sort of a cost-benefit analysis. So here are the benefits. Here are the drawbacks to using this funny coordinate system. What we're going to see is a lot of this stuff, a lot of these variables, the components become much simpler in a rotated coordinate system. So the first one is that the normal force, that pushing contact from the ground, is just always going to be equal to 0n. The second benefit is that the acceleration vector, so look at this example here. What are the directions that this can move? It can only move along the surface, you know. It can only move parallel to the surface. If it moved any way that wasn't parallel to the surface, it would be either jumping off the surface or sinking in, and it can't do that. And so the acceleration vector has to be parallel to that surface, which means it can only have an x component. So the acceleration vector is always going to be a0. This variable a can be positive or negative. We'll just solve for that in a problem. In this normal force, this variable n has to be positive. That's a pushing contact, so we know the direction of that force. There's one drawback. So these two things get simpler than they would be if we used a standard coordinate system. The drawback is that now that the coordinate system is tilted and the weight force is still acting straight down, representing the weight force vector is going to be messy now. We're going to have to use cosine and sine. So the one drawback is representing the weight force requires using cosine and sine. So let me do an example. So let's say that we have a 45-degree incline. And a 50-kilogram cart. And there's a force parallel to the surface pushing the cart up the incline of 100 newtons. And we want to figure out the acceleration vector. Well, we have to choose a coordinate system, so the y-axis is going to be pointing out of the surface. The x-axis has to be pointing down then, down the ramp, parallel to the surface. And we're going to use Newton's second law, so we'll start with a free body diagram. There's a weight force. That's 50 times 9.81, so 490.5. There's a force applied parallel to the surface of 100 newtons. Then there is a pushing contact from the ground. That's perpendicular to the surface, and I'll call that N. Any other forces acting on the boundary? Nope. So now we'll go to Newton's second law. In this green coordinate system, how do we represent this normal force? 0n. That's how it's always going to show up. How about that 100 Newton force? Close. It's in the negative x direction. It's pointing opposite the positive x direction. So that's going to be negative 100, 0. Now we have to deal with that weight force, and that's where the trade-off is that by rotating the coordinate system, we make the weight force get messier than it would be in a standard coordinate system. So the weight force looks like this. It has a magnitude of 490.5. And the coordinate system is this. There's the x-axis, there's the y-axis, and this angle is 45 degrees. That's the angle between the negative y-axis and the weight force. So what's the angle we want to calculate these components?
I'm sorry, how do you know that's 45 degrees?
I think the easiest way to think about it is to imagine starting with the standard coordinate system and then rotate it so that it's lined up with this. So we're going to start like this, rotate 45 degrees down. As you do that, the negative y-axis rotates 45 degrees over.
Okay.
But this also is what's going to happen every time. Whatever the angle is of that incline, okay, that's how much this angle is going to deviate. You know, that's how big the angle is going to be from the negative y-axis to the weight force. That's going to just happen over and over again.
Okay.
The real question is, based on which way the incline is slanted, is it 45 degrees less? You know, is it that angle less than 270, or is it bigger than 270? In this case, to go from the positive x-axis to the weight force, you have to, you know, go all the way around. There's 270 plus 45, so it's 315.
Okay.
Any other questions about that? So this angle is 315 degrees. And so the weight force is 490.5 times cosine of 315, 490.5 times sine of 315. And that says 346.84. Oh, and then I guess 346.84 negative. So that's all the forces. And Newton's second law says all the forces are equal to the mass of the chosen object times the acceleration vector. How am I going to represent the acceleration vector? A0. Yep, that's how we always do that one. So Newton's second law gives two equations. The x equation says negative 100 plus 346.84 is equal to 50a. So 246.84 is equal to 50a. So a is equal to 4.94. meters per second squared. And now we take this variable value and plug it into the acceleration vector. This is the acceleration vector. So the acceleration vector is 4.940 meters per second squared. And then the y equation says n minus 346.84 is equal to 0. If you wanted to use that to calculate the force applied by the ground, you could. All right, so I have a question about this acceleration vector. Is there any way for us to know whether the object is speeding up or slowing down? Well, first let me draw this vector. Okay, so this is in the positive x direction. So that means it's accelerating down the ramp. I don't think I said anything. So it's on the ramp, but I didn't say anything about what direction it's going. So that's the key question. So do you, is there any way to know whether it's speeding up or slowing down? No, there's not, because I didn't say anything about which direction it was moving.
Can't you guess because 100 Newton applied toward that?
Well, no, you can't, and that's a good question. So where would say it was moving up the ramp or down the ramp, where would that velocity come from? That velocity, the motion of the object at that instant, comes from the forces that were applied to it up until that instant. So this thing could be, for a month before this, you could have had 1,000 newtons applied going down. It's just picking up speed second after second for a month, you know? And then all of a sudden, you drop that force, that 1,000 Newton force that's been going for a month. This is a really long incline. And you apply this 100 Newton force here, but it's going like 1,000,000 miles an hour by then, you know? So if that's what you did, the snapshot that you would see is this thing moving really fast down the ramp that way, even though 100 Newton force is pushing it up that way. Okay? You also could have, for a month, been applying a force this way, and it would be going really fast up the ramp. And depending on which one of those two situations you were in, you'd have a different answer for whether it's speeding up or slowing down. We know that the acceleration's this way. If the velocity was this way, it would be slowing down. And if the velocity is this way, it would be speeding up. Any questions about that? Let me do one other one. So this time, the ramp is going to face this way. Let's say this angle is 20 degrees. And the mass of this cart is 2 kilograms. There's no other external forces applied, and we want to know what's the acceleration vector. So the first thing we have to do is choose this rotated coordinate system. The y-axis points right out of the surface. And then which way does the x-axis point? Up the ramp or down the ramp? Up.
How do we know that?
Because allowable coordinate systems are only rotated versions of the one that we're used to using. So you can rotate the coordinate system like this, but if I had put the x-axis down that way, there's no way to rotate this and end up with the y-axis up and the x-axis that way. Okay.
Yeah.
So it's because you're not allowed to flip those axes. You can only rotate them. Okay, so now a free body diagram of the cart. there's a weight force of 2 times 9.81. And then there's a normal force perpendicular to the surface. There are no other forces acting on the boundary. So now Newton's second law says 0n, and you could figure, you could look at this as the n is acting in the positive y direction, but you can also just remember that the normal force is always going to appear if you rotate the coordinate system in this way. The normal force is always going to be 0n. And now we have the weight force. So let's think about that. It's acting straight down with a magnitude of 19.62. And our coordinate system looks like this. There's the x-axis, y-axis. There's the negative y-axis. The angle between the negative y-axis and the weight force is 20 degrees. Okay, so what's the angle now from the positive x-axis to the weight force? Yeah, 250. Yep, exactly. So this time, the other one, we started at the positive x-axis and had to go past the 270 to get to it. In this case, because the incline is oriented the other way compared to horizontal, we start at the positive x-axis, go 90, 180. We don't make it to 270. We're 20 degrees short. So it's 90, 180, 270, minus 20 gives us 250. Or you could go the other way and go negative 90, negative 20 gives you negative 110. Those give the same answer. Yep.
So how did you know putting an origin tilting y to that direction? Or other one we tilted to the opposite direction?
Yeah, the y-axis always points straight out of the surface. Okay. Yes?
And can you always assume, if you have the graph, you tilt it this way, that it's adding that?
Yes, that's right.
It's tilting this way, it's subtracting?
Yep,
Okay.
that's right. Okay, so the angle here is 250. And so the weight force is 19.62 times the cosine of 250. 19.62 times the sine of 250. Can someone multiply those out for me? I don't have that here. Negative 6.71. 18.44. Thanks. Okay, so those are the only two forces acting. How do I know that these are the only two forces acting in Newton's second law? Yeah, I mean, I was just going to say because the whole reason to do that free body diagram is anything that appears as a force in Newton's second law appears in the free body diagram. That's the point of it, So once we've gone through all the forces in the free body diagram, we know we're done with this. And then that's equal to the mass of the object times the acceleration vector. How do I represent the acceleration vector? A0, yep. So the x equation says negative 6.71 is equal to 2a. And so a is equal to negative 3.6 0.35. Then to get the acceleration vector, we plug it into this. So the acceleration vector is negative 3.350 meters per second squared. So which way is that? Is that up the ramp or down the ramp? Yep. So 3.35 meters per second squared down the ramp. If the object at the time that this is happening is moving down the ramp, is it speeding up or slowing down? Speeding up if they're in the same direction. And if the object's moving up the ramp, then it's slowing down. Yes?
I know that you listed as one of the rules that the acceleration vector is always going to be a0.
Yes.
I guess I mean, if that's just a rule and you just have to not have an explanation, but for the y equation, wouldn't it turn out like y equals the natural force minus 18.4 equals 0? So then wouldn't it?
So yeah, let's. I'm going to write that y equation. That y equation here says n minus 18.44 is equal to 0. And so n is equal to positive 18.44 newtons. Okay, so yeah, you could use that to calculate the force that's applied to the cart by the incline. That's not an acceleration, though. That's a force.
Oh, okay. Thank you.
Yep. So accelerations and forces both appear in Newton's second law. And one way that they get sort of muddled, it's easy for them to get muddled in your mind, is that gravity causes this free fall acceleration. And it also applies a force all the time. And so you sort of lump these two things together. But forces are one thing, accelerations are a different thing. And just try to remind yourself that, you know, those are not in the same category. Any other questions about this example? Okay, so now we're going to use this for one more thing, for friction calculations. Is something coming, like feeding back? Is that super annoying? I'll bet. Well, I can't do anything. I could try to make a more annoying noise to cover it up. Okay, so friction, you can break up friction into two different categories. The first one is called static friction. That is the friction force that prevents an object from starting to move. So static friction is what you use if the object is at rest at the instant that if it doesn't have any velocity at the instant that you're looking at. Static friction just applies whatever force is required to prevent motion up until a maximum value. And so the magnitude of the static friction force is less than or equal to a coefficient. That's the Greek letter mu. It looks like somewhere between an M and a U, and it's spelled MU. So that's how you can remember it. And mu sub s, so it's the static, this is a static coefficient, times the normal force. This we're not going to be interested in. And then the other type of friction is kinetic friction. Kinetic friction is a force that tries to slow moving objects down. This one doesn't have any possible range of values. The static friction has a whole range of values, anywhere from 0 all the way up to this coefficient times the normal. Kinetic friction always has the same magnitude, and that magnitude is equal to a coefficient. It's the Greek letter mu, but this time we'll use the subscript k for kinetic, times the normal force pushing the two surfaces together. Okay, this is the one we're going to look at. We're not going to do static friction. But it's worth mentioning that the coefficient of static friction is always bigger for two materials than the coefficient of kinetic friction. And so you have experience with this. If you think about like a big moving box full of stuff sitting on the floor, say it's got all your heavy stuff in it, you know, books or whatever, it's heavy. To get it moving is hard, you know. And when you do get it moving, you feel something kind of like pop free, you know. And then once you get it moving, it's easier to keep it moving than it was to get it started. That's because static friction force has the ability to be bigger than the kinetic friction force. The reason for that is if you think of friction as just being all these little molecular entanglements between the two surfaces that are sliding against each other. If you let two things sit next to each other, the little fingers get into all the grooves and they get a tight grip on each other. If the things are just sliding by each other, they don't have a chance to ooze into all the crevices and whatever. And so the entanglements just aren't as strong. And that's why it's easier to slide two objects than to keep them sliding than it is to start them sliding against each other. The kinetic force of friction it would. It's still harder to make something heavier accelerate, you know, because of Newton's second law. But yeah, without friction, any tiny amount of force you apply to anything of any size will make it move. It'll just make it accelerate a lot less if it's heavy. I don't know. I don't know if they kept this forever, but do any of you remember the Science Museum in St. Paul? I remember, this was like when I was a kid, so I don't know. But they used to have this exhibit where they had like a semi-truck smushed into a cube. So it was super heavy, you know, really a lot of mass. And they had it resting on this sled that when you pressed a button, it was like air hockey, you know. It used jets of air to reduce the friction between this semi-truck and the ground to almost nothing. And if you did that, you could move this semi-truck. Like, you didn't have to apply much force to get it moving, but you couldn't move it very fast. It accelerated really slowly because it had a ton of mass. And then if you took that off, you couldn't move it at all. You know, the friction just totally prevented it from sliding. Anyone seen that thing? So the kinetic force of friction is a force vector. And so a force vector, any kind of vector, has two properties, right? It has a magnitude and a direction. So the direction of that friction force vector is opposite the direction of the velocity. And so why is that? Well, I mentioned that kinetic friction is always trying to slow objects down. So if you're trying to slow something down, you apply a force in the opposite direction of the velocity, and that's what friction always does. If friction ever applied a force in the same direction as the velocity, you'd have things where, like, you could use friction to make something speed up, you know, rocket away. That would be cool, but that's not the world we live in. Like, yeah, I supercharged my car with extra friction. So that's the direction, and then the magnitude is mu sub k times the normal force. So how do you get that mu sub k? What is that mu sub k? So mu sub k is called the coefficient of kinetic friction. And it's something that you just look up for the two materials that are in contact, you know, that are sliding against each other. So you can just Google coefficient of sliding friction for wood and steel or something, and it'll just give you a value for this. Or you can look up the coefficient of sliding friction for ice and, you know, rubber or something. And for every pair of materials, there's just a different value for that. So now, what are the units of the coefficient of friction? There's no units, that's right. So how can you tell that? So it's a coefficient, so you might think there's no units. That's a reasonable thought. But you can actually use the magnitude of the force of friction to figure out that there are no units. We know that the magnitude of the friction force is this coefficient times the normal force, right? We know that the magnitude has to have units of newtons. It's a force, right? The friction force is a force, so it has to have units of newtons. We know that the normal force has units of newtons. And so what can you multiply by newtons to get newtons? It just has to be a number. It can't have any other units. So this is just a unitless number. In most cases, it's less than 1, but that's not a rule. Some pairs of materials actually have coefficients of friction quite a bit higher than 1. And so now I'm going to go through an updated list of the things we know so when we do friction problems, we're still going to use that rotated coordinate system. So here's an updated list of variables in the rotated coordinate system. We know that the normal force is 0n. We know that the acceleration vector is a0. And now if the friction force is acting, so the velocity has to be along the surface. The friction force then has to be along the surface too. So what do we know about the components of the friction force vector? To be along the surface, it has to have an x component only. And so this is going to be plus or minus coefficient times normal for the x component, and then 0 for the y component. And this has to be opposite the direction of the velocity. Yeah, it's always going in the opposite direction of velocity because it's always trying to slow it down. Okay, so now let's say we have an incline that's at 20 degrees. And a 10 kilogram object. And let's say the motion is up the ramp at this instant. That tells you the direction of the velocity vector. And let's say there's a downward, not downward, but toward the surface, pointing towards the surface, a force of 100 newtons. And we want to calculate two things. What's the acceleration vector if the contact is frictionless? And then second, we want to calculate the acceleration vector if the coefficient of friction is 0.1. Okay, so for part A, we're going to assume that there's no friction. There's a weight force of 10 times 9.81. There's a pushing force, I'll call N. And there's a force opposite the contact force of 100. And that's all the forces acting. Any questions about the free body diagram?
So the motion doesn't have a force?
Right. No. So Newton's second law says, well, I didn't draw the coordinate system. The coordinate system is going to look like this. The y-axis out of the surface. The x-axis down the ramp. So that 100 Newton force is in the negative y direction. So 0, negative 100. The normal force is 0n. the weight force has a magnitude of 98.1. And this angle is 20 degrees. So what's the angle? 290, right. So from the x-axis you go around to 270 and then you go 20 degrees more. So 270 plus 20 is 290. Or negative 70 works the same. And so that weight force is 33.55, negative 92.18. And all that is equal to the mass times the acceleration vector, a0. So the x equation says 33.55 is equal to 10a. So a is equal to 3.355 meters per second squared. And now to get the acceleration vector, you just plug it back in there. The acceleration vector is 3.355 for an x component, 0 for a y component. Okay, so is this speeding up or slowing down? Well, what direction? Let's just draw. The positive x direction is down the ramp. We have a positive x, so it's this way. Yep, the velocity vector was up the ramp, so this is slowing down. Okay, so now we're going to do the friction calculation. Any questions? Anybody have any questions? Yeah.
Why did you write that magnitude down, though?
Because that, when we calculated this acceleration vector, we got something in the positive x direction. And the positive x direction goes down the ramp. Any other questions? All right. So what do you think is going to happen when we add friction to this? Do you think this acceleration is going to be bigger, smaller, different direction? What do you think is going to happen? Smaller acceleration. So it's actually going to be bigger in this case, and the reason is, the thing you have to think about is that acceleration can make something speed up or slow down. Friction is always trying to slow things down. And so if this thing is already slowing down even without friction, it's going to slow down even more when we add friction. Okay? So the fact that this was already slowing down before there was any friction put in means that that number is going to get even bigger in this same direction when we add friction. Is that confusing? Yes, it is. Liars. In the same, it's going to, this acceleration is going to be bigger, but in the same direction as the acceleration was in part A when there was no friction. Meaning it's going to slow down faster, you know, because friction is going to help it slow down. Yes. it would either go down or possibly change into the other direction, and it would either speed up less or start slowing down. Yep. But what you can't ever have is friction make something speed up more. I know. Well, so far we haven't figured out a way. Okay, so for part B, now we're going to add friction. Okay, so free body diagram. There's a weight force of 98.1. There's a pushing force from the ground. There's that pushing force from above, pushing it into the ground. That's 100 newtons. And now we also have to deal with that friction force. The friction force has a magnitude of mu times the normal. So in our case, that's 0.1 times this n. And it's in the opposite direction of the velocity. What's the direction of the velocity in this problem? It's going up the ramp, so the friction force is going to go down the ramp. And so there's a friction force like this with a magnitude of 0.1 times n. That was given in the problem. The coefficient is 0.1. Almost always, I mean, I think in every problem that you're going to have to do, that's something that's just given. It's like something that you looked up, you know. So now Newton's second law. We have 0, negative 100, plus 0n, plus 0.1n. What's this in components? So look at what direction the positive x-axis is. Is it in the direction of positive x or negative x? That's the question. It's positive x in this case. So in components, this is 0.1 n 0. And then we have the weight force. Well, the weight force is the same as it was before, so I'm just going to enter that in. You know, friction doesn't affect the weight of this object. So plus 33.55 minus 92.18. And all that is equal to the mass times the acceleration. No, because we're trying to find the new A now. The acceleration is going to be different now that there's friction. Okay, so we have two equations. The x equation says 0.1 n plus 33.55 is equal to 10a. And the y equation says negative 100 plus n minus 92.18 is equal to 0. When there was no friction, we could just go right to the x equation and solve for a. We can't anymore because now there's an n in there that we don't know yet. And so the approach we're going to take is the same as with all of these problems. We're going to use the y equation to find n, and then plug that n value into the x equation. So first, the y equation for n, and then plug n into the x equation. So the y equation says n is equal to 192.18. And so now if we plug that into the x equation, we get that 0.1 times 192.18 plus 33.55 is equal to 10a. Everyone follow where this equation came from? Okay, so this says 19.22 plus 33.55 is equal to 10a. That says 52.77 is equal to 10a. And so a is equal to 5.277 or 5.28 meters per second squared. Now we plug that a value into the acceleration vector. And the acceleration vector is 5.280 or 5.28 in the positive x direction. Okay, so did this do what we expected it to do? Yeah, the velocity vector is up the ramp, so this is slowing down. And the magnitude of the acceleration is bigger once you add friction than it was without friction, which means it's slowing down more quickly once you add friction than it is without. And that's what friction does. It slows things down. Okay, so a general thing to notice in friction problems, always solve the y equation for the normal force, and then plug that normal force into the x equation to find the acceleration. Let me do one more example problem. So let's say this incline is 30 degrees. And let's say there's a 1 kilogram block that's connected to a cable. That cable goes over a pulley and then connects to a hanging block of 2 kilograms. And let's say that at this instant the motion is up the ramp. What's the acceleration vector of the 1 kilogram block? Oh, yeah. So the coefficient of friction, let's say it's 0.2. One thing that we're going to do in this, I can't remember in this section if we've done this or not. Have we done problems where two things are connected over a pulley like that? Yeah. Okay. So the thing that's going to come up is the accelerations of these two are not independent, right? If this thing moves an inch that way, this thing moves an inch down. And so whatever the acceleration of this is up the ramp, the acceleration of this has to be down, all right? And so we're going to use the same variable a to represent both of these two accelerations, but we're going to use them a little bit differently because this can only accelerate along the incline, and this can only accelerate up and down. So when we get to that, we'll have to be careful about it. Also, when I isolate the block that's on the incline, we're going to use this coordinate system that we've just been talking about. But when we use when we isolate the hanging mass, we're going to use a standard coordinate system. Okay, so I'm going to start with a free body diagram of the block on the incline. There's a weight force of 1 times 9.81. There's a normal force. There's a cable tension. So if I say to include a little stump of the cable there, and then the force comes out of the stump. So I'll call this T. We don't know what that is yet. And then the last thing is there's a friction force that's opposite the direction of motion. So it's this way, and it has a magnitude of the coefficient times n, so that's 0.2 n. And then Newton's second law says, well, that tension force is in the positive x direction, so T0. The normal force is in the positive y direction, so 0n. The friction force is in the negative x direction, so negative 0.2n 0. And then the weight force is in this direction, where there's the coordinate system. And this angle is 30 degrees. So what's the angle that we're going to use for those components? It's actually 300 because you start here, you go counterclockwise, you hit the 270 line, and then you have to keep going to get to the vector.
Yeah, I thought the coordinate system was the other way.
Oh, I did it backwards.
Okay.
Because I'm a stupid idiot. No, it's unacceptable. $240, you're right. Okay, so theta is 240. And so then the weight force is 9.81 times cosine of 240, 9.81 times sine of 240. Can someone calculate that? Okay. 496. Okay, so add in the weight force. That's all the forces. And so then those, those are equal to the mass times the acceleration vector that I'm still just going to call A0. The x equation says T minus 0.2n minus 4.905 is equal to A. The y equation says n minus 8.496 is equal to 0. So like we always do with these friction problems, I'm going to solve for n and then plug it into the x equation. So n is equal to 8.496. And then I'll plug that into the top equation, and it says T minus 0.2 times 8.496 minus 4.905 is equal to A. And I'll rewrite this as, can someone calculate, okay, I'm going to rewrite this as T minus A is equal to 4.905 plus 0.2 times 8.496. Can someone tell me what that all comes to? Point 6.6042. Okay. Okay, so look at this equation. Is there anything we can do with this? No, we already used the y equation, so we're left with one equation that has two variables in it. So I'm just going to circle this, call it equation star, and set it aside. What we're going to end up with is when we use Newton's second law on the hanging mass, we're going to get a second equation that lets us solve for these two variables. Okay? So that's all we can do for now. So now a free body diagram of the 2 kilogram mass. There's a downward force of gravity. That's 2 times 9.81, so 19.62. And then an upward force, T. Why is that the same tension as the force for the first mass? It's the same cable, yep. As long as that cable only goes over pulleys, it's the same value. And so Newton's second law says, now we're using the usual coordinate system. So 0t plus 0, negative 19.62 is equal to the mass times, now we have to think about what the acceleration is. If the first block has an acceleration, so say that variable A is positive, okay? That means that first block is accelerating in the positive x direction. Okay? Like, imagine this a is positive 1. That means this would be accelerating in the positive x direction. So if this has an acceleration of positive 1 in the x direction, what are the components of the acceleration of this one? That's the question. Yeah, this would have an acceleration of 1 in the negative y direction. And so I'm going to represent the acceleration of that hanging mass as 0, negative a. Okay? Anybody have any questions about that? That's the relationship between those two accelerations. So 0, negative a. The x equation says 0 equals 0, so that doesn't help. But the y equation says t minus 19.62 is equal to negative 2a. And I can rewrite that as t plus 2a is equal to 19.62. I'll call that equation double star. And now I have these two equations, star and double star. It's two equations for the same two variables. So we can solve those. Okay? You can do it by substitution. You could also do it by subtracting one equation from the other. Whatever you feel comfortable with. Substitution always works, so that's probably a good way to go. I'm going to do it like equation star minus equation double star. So that says, so if we take this minus this, we have t minus t is no t's left. And then minus a minus 2a. So minus 3a is equal to 6.6042 minus 19.62. Can someone subtract that? Oh, I can do that. That's 13.02. Negative. And so A is 13.02 divided by 3. What's that? Positive because both sides are negative. So 4.34. And then finally, to get the acceleration vector, you plug this value back into the vector that's in Newton's second law, and you get an acceleration vector of 4.340. Or, in other words, an acceleration this way of 4.34. So is the block speeding up or slowing down? Speeding up because that acceleration is in the same direction as the velocity vector.
How is the acceleration pointing that way when the cable is horizontal?
The cable is parallel with the ground. Yeah. Any other questions? Yes, very good. Then you plug A into that value of A into the 0, negative A to get the acceleration. Yep. Okay, have a good weekend.